Imagine stepping into a machine, pressing a button, and suddenly finding yourself 100 years into the future. Or perhaps back in ancient Egypt, watching the pyramids being built. For centuries, humanity has dreamed of bending time itself. Time travel has fueled some of our most creative works of fiction. Doctor Who, Back to the Future, Interstellar, and countless novels and films. But beyond the silver screen, there's a serious question. Could time travel actually be possible? At first glance, the idea seems absurd. Time feels like an unstoppable river, always flowing forward. Unlike space, where we can move in any direction, left, right, up, down, time appears to allow only one movement: forward. We're all passengers on this train, and there's no turning back. But over the last century, modern physics has revealed something startling. Time is far stranger than common sense suggests. Albert Einstein's theories of relativity showed us that time isn't a universal constant. Instead, it stretches and bends depending on speed, gravity, and energy. This means that under the right conditions, we can actually manipulate how time passes. In fact, we already know how to travel into the future, at least in limited ways. But traveling to the past? That's where the science becomes murkier, and the paradoxes begin. Why this matters? The question of time travel isn't just science fiction fun. It's deeply connected to some of the biggest mysteries in physics. The nature of time itself, the fate of the universe, and whether reality is deterministic or full of branching possibilities. Understanding whether time travel is possible forces us to test the very limits of relativity, quantum mechanics, and cosmology. If we're going to ask whether time travel is possible, we first need to understand what time actually is. At first glance, that may seem obvious. Time is the ticking of a clock, the rising and setting of the sun, the hours and minutes we use to schedule our lives. But in physics, time is much more complicated. For centuries, scientists thought of time as absolute. In Newton's mechanics, space was like a great stage where events happened, and time was the clock that ticked equally everywhere. To Newton, a second on Earth was the same as a second on Mars, or near a star, or in empty space. This view worked perfectly well for centuries. It described falling apples, orbiting planets, and the motion of objects. But in the early 20th century, Albert Einstein challenged that picture with his theory of relativity, and with it, our understanding of time changed forever. The birth of relativity. In 1905, Einstein published the special theory of relativity. It was built on two postulates. The laws of physics are the same for all observers moving at constant speeds. The speed of light is the same for all observers, no matter how fast they're moving. These two statements may sound simple, but they completely overturned Newton's picture. If the speed of light is constant, then time itself has to bend to make the math work. Imagine two observers, one standing still, one racing close to the speed of light. They each carry a clock. According to relativity, the moving observer's clock will tick more slowly compared to the stationary one. This effect is called time dilation. You might think time dilation is just a theory, but it's been tested again and again. In 1971, physicists Joseph Huffell and Richard Keating flew atomic clocks on commercial airplanes around the world. When they compared the flying clocks to identical ones left on Earth, they found the airborne clocks had lost or gained time exactly as relativity predicted. Even more impressive, modern GPS satellites must constantly correct their onboard clocks. Because they orbit high above Earth, where gravity is weaker, their time runs slightly faster than ours on the surface. If engineers ignored this effect, GPS would drift by kilometers every day. That means every time you use Google Maps or a navigation system, you're relying on relativity and on the fact that time really does bend. Time as part of space-time. Einstein's later theory, general relativity, went even further. In 1915, he showed that gravity is not a mysterious force pulling objects together. Instead, it is the curvature of space and time itself. Massive objects like stars and planets warp the space-time fabric around them, and smaller objects simply move along the curves. This means that time is not separate from space. They are deeply connected in what we call space-time. Just as space can bend and stretch, so can time. A universe without absolute time. The consequences are profound. There is no single universal now that applies everywhere in the cosmos. Two observers moving differently may disagree about the order of events. For one person, event A might happen before event B. For another, moving differently, event B could appear to happen first. This doesn't break causality within each person's perspective, but it shows how strange time becomes at cosmic scales. Building toward time travel. So, what have we learned so far? Time is not absolute. Time moves at different rates depending on speed and gravity. Experiments confirm this every day, from atomic clocks to GPS. This means that, in a sense, time travel is already real. Astronauts on the International Space Station orbit Earth at 28,000 kilometers per hour. Because of time dilation, when they return to Earth, they've aged a little less than the rest of us, by milliseconds, but still measurable. Of course, that's just a tiny effect. But the physics suggests that if we could push these differences to extremes, like traveling close to the speed of light or hovering near a black hole, the time gap could become enormous. This brings us to the next step: time travel into the future. In this documentary-style deep dive, we'll explore the question of whether time travel could be possible. To do that, we'll break the journey into 5 major topics. Time and physics. How scientists understand time, from Newton to Einstein. Time travel to the future. What relativity teaches us about reaching forward in time. Time travel to the past. The strange and controversial ideas about reversing the arrow of time. Paradoxes and problems. Logical puzzles that challenge the very concept of time travel. Current research and the future. What cutting-edge physics says about whether we'll ever build a time machine. By the end, we'll see that while time travel to the future is not only possible but already observed in experiments, time travel to the past remains one of the greatest scientific and philosophical mysteries of all time. So before we dive into wormholes, paradoxes, and futuristic theories, we need to step back and ask, what exactly is time? How have scientists gone from seeing it as absolute to realizing it's flexible and intertwined with space? That's where our story begins. If time moves differently depending on speed and gravity, then one form of time travel is already scientifically proven: traveling into the future. Relativistic time dilation. Let's imagine a spaceship capable of traveling at 99.9% the speed of light. The crew on board would experience time normally. To them, days and weeks would pass just as usual. But back on Earth, years, or even centuries, could go by. This means if astronauts set off on such a journey, they could return to find that Earth has aged far more than they have. In a sense, they've traveled into Earth's future. This isn't speculation. The math of relativity makes precise predictions, and experiments confirm them. Particle accelerators show this effect clearly. Subatomic particles called muons normally decay in microseconds, but when accelerated to near-light speeds, their lifespans stretch out dramatically. That's time dilation in action. Gravitational time dilation speed isn't the only way to affect time. Gravity can too. According to general relativity, the stronger the gravity, the slower time runs. This has been demonstrated in labs by comparing super-precise atomic clocks at different altitudes. A clock at the bottom of a tall building runs ever so slightly slower than one at the top. On cosmic scales, this effect becomes dramatic. Near a black hole, time slows so much that an outside observer could see you frozen, while you experience only minutes. This idea was famously illustrated in the film Interstellar, where astronauts visiting a planet near a black hole experience hours, while decades pass for their colleagues outside. And remarkably, this is rooted in real physics. Astronauts as time travelers. Even today, astronauts experience tiny amounts of time travel. Russian cosmonaut Sergei Krikalev, who spent 803 days in space, is technically about 1/5 of a second younger than if he had remained on Earth. That may not sound like much, but it proves the principle. There's a catch. While traveling to the future is possible, you can't come back. Time dilation only moves you forward relative to others. Once you've jumped ahead, there's no known way to rewind. But what about traveling backward? That's where things get tricky. Time travel into the past is far more controversial. While relativity allows certain mathematical solutions that seem to permit it, these scenarios often come with huge problems. Closed time-like curves. In relativity, a closed time-like curve is a path through space-time that loops back on itself. If such a curve existed, you could in theory return to an earlier point in your own history. Some solutions to Einstein's equations allow for this. One example is Gödel's universe, a model discovered by mathematician Kurt Gödel in 1949. In his solution, the universe rotates, creating paths that circle back in time. Another is the Tipler cylinder, a hypothetical, infinitely long rotating cylinder that could drag space-time around itself. Wormholes. Perhaps the most popular theoretical time machine is the wormhole. A wormhole is a tunnel through space-time connecting two distant regions. If one end of the wormhole experiences time dilation, say, by being moved near a black hole, then stepping through could, in principle, let you exit at a different time. Physicists like Kip Thorne have explored these ideas seriously, but building or stabilizing a wormhole would require exotic matter with negative energy density, something we don't yet know how to produce in useful quantities. Problems with past travel. The biggest issue with past-directed time travel is paradoxes. If you could go back in time, you could potentially change events that already happened. This leads to contradictions like the famous grandfather paradox. If you went back and prevented your grandparents from meeting, how could you exist to travel back in the first place? We'll explore paradoxes more in the next section. But suffice it to say, time travel to the past, while mathematically possible in some models, seems to clash with both physics and logic. The appeal of time travel is obvious, but the paradoxes are equally notorious. The grandfather paradox. This classic paradox asks, what happens if you go back in time and prevent your own birth? If you succeed, you'd never exist to go back in the first place. This creates a logical contradiction. The bootstrap paradox. In this paradox, information or objects appear to exist without origin. For example, you travel back in time with a famous book, give it to its author, who then publishes it. But where did the book originally come from? It has no point of creation. The arrow of time physics also tells us that time has a preferred direction, forward. This is tied to entropy, the tendency of disorder to increase. Breaking this arrow of time would require reversing entropy, a feat that appears impossible according to the second law of thermodynamics. Possible resolutions. Some physicists propose that paradoxes might be avoided by the laws of physics themselves. The Novikov self-consistency principle suggests that even if time travel to the past is possible, events would conspire to prevent contradictions. You could visit the past, but you wouldn't be able to change it. Others look to quantum mechanics. The many worlds interpretation suggests that every possible outcome of an event exists in its own branching universe. If you went back in time and altered something, you wouldn't change your own timeline. You'd create a new one. Where physics stands. So, where are we today? Time travel to the future is a fact of physics, confirmed by relativity and experiment. Time travel to the past remains speculative. Wormholes and closed time-like curves appear in solutions to Einstein's equations, but stabilizing them likely requires new physics. Quantum gravity and beyond. Many researchers believe that a theory of quantum gravity, a unification of general relativity and quantum mechanics, will be needed to truly answer these questions. Some models suggest that space-time is granular, or that causality is more fundamental than time itself. Philosophical implications. Even if we never build a time machine, the study of time travel forces us to confront profound questions. Is time real, or an illusion? Is the future already determined? Do alternate universes exist? So could time travel be possible? The honest answer is, partly. Traveling into the future is not only possible but unavoidable. It's happening right now thanks to relativity. Traveling into the past, however, remains one of the great mysteries. It may require physics we haven't yet discovered. But one thing is certain: the more we study time, the stranger it becomes. And in the words of Einstein himself, the distinction between past, present, and future is only a stubbornly persistent illusion. Time travel may remain a mystery, but the journey to understand it is just beginning. If you enjoyed exploring this question with me, make sure to give this video a like. It really helps the channel grow. Don't forget to subscribe and hit the bell so you never miss future explorations into the universe, physics, and the mysteries of reality. If you want to keep traveling with us, check out one of these videos next. Until then, keep questioning, keep imagining, and keep looking up at the stars.